Welcome to this short introduction to Border Gateway Protocol, or BGP. This is a very important protocol that provides the foundation for internet connectivity, but it's also very complicated and different from other routing protocols. My goal with this video is to answer some of the more basic questions about BGP and cover a few of the basic topics. This is not by any means designed to be a comprehensive video about BGP. I'm primarily aiming this video at those studying for their CCNA who need a quick resource focused on BGP specifically. I assume that level of familiarity with the other concepts touched on in this video. As I mentioned before, our goal is to answer some basic questions about BGP, including how does BGP differ from interior gateway protocols or IGPs? How does BGP establish adjacencies and go about sending or receiving routing information? How does BGP determine the best path to a given prefix or network? How does BGP prevent routing loops? I answer each of these questions in this video. Let's start with the first one. If you've read about routing protocols, you've likely gotten the impression that BGP is special for some reason. But why is that? Well, BGP was designed with different goals in mind than the other routing protocols you've likely seen so far. I wanted to take a moment to dive into what those specific differences are. First, let's review what IGPs are used for. For the most part, IGPs are designed to provide full and dynamic reachability between networks. Routers usually discover each other automatically, and the end goal is full reachability between all networks. IGPs typically heal from network outages quickly, as any disruption in reachability would impact many end hosts. They do this using some sort of basic routing metric. For distance vector protocols, this is a distance, like a hop count in RIP or a composite metric in EIGRP. For link state routing protocols, this is a cost associated with an interface. In both cases, the metric is relatively flat and straightforward, providing the ability for routers to move fast. Finally, IGPs aren't without faults. Distances, topology tables, and link state databases can only be so large, so while IGPs are fast, the trade-off is that they can't remain fast as more routers are added. At some point, larger networks start to run up against these scaling limitations. What can we do about that? Well, that's where we're headed next. BGP has a very different set of goals than IGPs. First, it provides a summarized view of prefixes for groups of routers. We call this group of routers under someone's control an autonomous system, or AS. An AS may be under the control of a company, a set of companies, or maybe even a small team. The main point is that routers outside of the AS are not under the control of that AS. That means they're primarily responsible for determining how they want to route traffic to other autonomous systems, and somewhat responsible for how other autonomous systems route to them. BGP provides autonomous systems with both the means to control how they route traffic and the means to influence how others route traffic to them. While IGPs have to start from scratch to provide connectivity, BGP assumes some IGP is already running underneath of it. This means that it can use plain old TCP connections to exchange routing information and doesn't need to implement its own mechanisms for reliability. IGPs focus on making quick routing decisions during outages and require detailed topology information to do this. That, in turn, limits scaling. BGP decides to forgo the level of detail seen in IGPs, which, in turn, allows for a much larger scale of the networks it can handle at a time. Finally, BGP can be used within an AS to act as a bridge between individual IGP domains. For example, you can run OSPF across all of the buildings at a site, and then use BGP between sites. This is especially useful if OSPF may hit scaling limits if it were run across the entire multi-site topology. With BGP, we can break the network into smaller chunks that are almost certain to operate within an IGP's scaling tolerances. Here's a quick visual of what BGP might look like in that last scenario. I've put a few different IGPs in this picture because I want to highlight that BGP doesn't care too much about the underlying IGP. In this example, we even have a mix of link state and distance vector routing protocols. BGP provides a common way for these protocols to talk to each other. This diagram is a bit vague. It could be showing different companies connecting to each other, or a single company using BGP to bridge several IGP domains, maybe as the result of an acquisition or merger. Really quickly, let's dive into some details about BGP's differences from IGPs. BGP is designed to transfer prefixes, not discover them, so routing adjacencies aren't typically dynamically formed like they are with IGPs. Instead, you, the network administrator, need to configure adjacencies individually and manually. Rather than configuring a network statement that matches some set of interfaces or just specifying that a routing protocol should run directly on an interface, you will need to configure neighbor commands that specify the IP address of the BGP neighbor. As we mentioned, BGP runs over TCP, specifically port 179. Many of the other IGPs you're familiar with operate directly over IP and use their own protocol number and mechanisms to ensure reliability. Since BGP uses TCP, it gets reliability for free as part of that protocol's use of sequence numbers. Like other TCP streams, BGP sessions can run on top of an IGP, even over several routing hops. Finally, because BGP depends on an IGP for connectivity, it doesn't think in terms of interfaces, but in terms of addresses. One of the things each BGP route will have is a next hop. This next hop address must be in the routing table and reachable by a protocol that's not BGP. If this isn't the case, the BGP route won't be considered valid and won't be installed. So we have the basics of what makes BGP different. Great. Now let's talk about how it transmits prefixes. As we've already established, BGP uses TCP, but this next section will dig a bit further into the specific messages BGP sends and receives over TCP. BGP uses 4 different message types to establish adjacencies and exchange prefixes. The first type, the open message, is used when a router is trying to establish a BGP session with another router. The message contains a few important details about the router and its capabilities. The most important of these is the AS number, router ID, and the session timers. A mismatch in the AS number with what's configured on the remote router will result in an error message that will cause the session to get stuck before it can be set up. The second type, the update message, is what's used to send routing information to the other router. You and I might think of each prefix as having a set of attributes, but in BGP, it's the other way around. A given set of attributes is mapped to a set of prefixes. If you think about it, this is a more scalable approach as it prevents duplicate sets of attributes from being sent for different prefixes. The third type, the keep alive message, is a very simple and straightforward message. There's no actual information in this message, it's just sent by routers to keep the underlying TCP session up. The last type is the notification message, which will only be sent when something is wrong. Maybe there's a problem with the open message, maybe some address family isn't supported, or maybe some mandatory attribute is missing from a prefix. Notification messages are how one router lets the other router know what the problem is. The diagrams in this slide and the next slide show the session setup process between 2 routers. The first 3 arrows in this slide show the typical TCP 3-way handshake, with each side synchronizing an initial sequence number and the other side acknowledging that sequence number. R1 happens to initiate the TCP sessions towards R2 in this instance, but in reality, both routers will attempt to establish the sessions in both directions simultaneously. Whichever session is set up first wins, and the other session is torn down. After this, both routers will send an open message to begin establishing the BGP session. In this diagram, I've shown that R1's open message is sent and acknowledged first, but either side might send and/or receive an open message first. If the other router, R2 in this case, accepts the open message, it will respond with a keep alive message to indicate that all received information matches the configured session. The process happens in both directions, and again, while this diagram shows the process serially with one direction being set up before the other, it's entirely possible and very likely to have this process happen in parallel, with open messages being sent by both sides and acknowledged by the other side in roughly the same time frame. Once the 2 routers have established that they accept the remote end's BGP parameters, they will send update messages to each other. Again, this diagram is oversimplifying things and showing one update in each direction serially. The reality is that there may be many more updates sent, and updates may be sent in parallel in each direction. Updates are sent via TCP, so there's an empty TCP acknowledgement I haven't shown, which would be sent back after each of the arrows in this diagram. In the meantime, the BGP sessions will continue to send keep alive messages as determined by the timer values in the open messages. I won't dive into the details on timers in this video. This will continue for as long as the session is established, which is usually until a link goes down or a notification message is received. So we've looked briefly at a successful BGP session, But what might cause session setup to fail? The first and most basic reason a session won't come up is that the TCP session can't establish. BGP relies on TCP, so if a TCP connection can't be successfully formed, BGP won't work. There are quite a few different reasons TCP might not be working. A very basic reason is that the router doesn't have a route to reach the BGP session's remote IP address, though this isn't likely to be the case for interface-based point-to-point sessions. Conversely, the remote router might not have a way to route traffic back to your address, or might not be listening for BGP connections on the address you specified. Finally, firewalls need to be configured to allow BGP sessions through, so if you have applied an access list, it may prevent the session from coming up if it doesn't allow TCP port 179. Assuming TCP is working, there could be some problem with the open message you're sending. Perhaps you made a typo in the autonomous system number, or your router is configured with some options that the remote end doesn't support or understand. Fortunately, these problems are somewhat easier to diagnose, as a notification message will be sent back to the offending router explaining what's wrong. Finally, there may be a problem with an update that's sent or received. Maybe some attributes are specified incorrectly, or you see information for an address family that isn't supported by the session. In any case, like the problems with open messages, these problems will cause a notification to be sent that is typically logged by both sides. Alright, we've been talking abstractly about attributes so far. At this point, I'd like to dive into what those look like and how BGP uses them to determine the best path to a given network or prefix. The key point of this session is that BGP has many more attributes than any IGP. This is primarily a side effect of BGP's purpose. Autonomous systems want a large amount of control over both ingress and egress traffic, and need flexibility in how that control is implemented. I'm not going to review all possible BGP attributes and their usage, but there are a handful of common attributes that I think every network engineer should know. The first of these is local preference. Local preference, or LP, is something that's set by network administrators to prefer a certain path for outbound traffic. When a prefix is received from a neighbor, it can be assigned a local preference value that's higher than others, and it will be preferred. The default LP on Cisco devices is 100. AS path is probably the most important attribute for BGP. You see, BGP is what's known as a path vector protocol, meaning that it doesn't just count hops as a numerical distance like a distance vector protocol. Instead, each prefix has a record of the path it traversed, from an AS perspective. That means that this attribute is going to be a list of the autonomous system numbers a route has traversed, starting with the most recent AS number and ending with the originating AS number. The length of this attribute, that is, the number of autonomous systems the prefix is traversed through, is used to determine which path is chosen for that prefix. A shorter AS path will be chosen over a longer one. I have a quick visual example of AS path on the next slide. The origin code is something that's set by the originating AS when it advertises the prefix to its neighboring autonomous systems. This is sort of an indicator of the reliability of a prefix. There are two values in modern networks: internally originated, which is represented with a lowercase I, and incomplete, represented with a question mark. Internally originated prefixes are typically matched specifically with a network statement, while incomplete prefixes are originated by redistributing routes from another routing protocol. Routers will prefer I routes over question mark routes, since matching with a network statement is considered more reliable than redistribution. The multi-exit discriminator, or MED, is also called the metric. This is how providers can influence traffic coming into their network. MED is sometimes called metric because it can be tied to the autonomous system's IGP metric for a given prefix. MED is completely optional, and by default it isn't set to any value. Opposite the behavior of local preference, a lower MED value will be preferred over a higher one. If you're using MED for IGP metric as I described, this makes a lot of sense. If your AS advertises a prefix with a higher IGP metric to one neighbor than another, you're going to want to take the better path or lower MED path. Finally, communities provide a way to tag traffic for some particular purpose. Most of them don't affect routing behavior on their own, but network administrators can use policies to specify certain actions to take on a prefix based on the community value. One value might increase the local preference, for example, while another may designate where a prefix can or can't be advertised. These communities can be set internally or externally to influence routing. There are a few communities that are well known, which are reserved for specific purposes. These don't need to be matched by a particular policy like the other ones. Instead, the router will take the appropriate action on its own. Here's that example of AS path I mentioned in the previous slide. You'll notice that I've included the internal origin code I at the end of the advertised path. This is the format that you'll typically see in a show IP BGP output on Cisco routers. Notice that the AS number is prepended when the prefix is advertised, not when it's received. Now let's talk about the actual best path selection process. You can find a massive 13-point tiebreaker article on Cisco's website, which I'll be sure to link in the video description. This is a great reference for more detailed BGP scenarios, but it isn't going to be asked about on your CCNA. Typically, the full document allows you to look at BGP routes and go down the list until you find a tiebreaker. For the most part, you only need to worry about the attributes we've talked about, plus one other thing called weight. I don't call weight a BGP attribute because it isn't one. It's something that's local to the router and is Cisco specific. Effectively, it acts just like local preference, but isn't advertised to any neighbors. The remaining attributes to remember are listed here and are evaluated in the same order we discussed in the previous slide. A great way to see these attributes briefly is with the show IP BGP command. You can optionally specify a prefix you want to look at, or you can just issue the command without a prefix to see these attributes for all prefixes. Here's an example of show IP BGP on a small BGP topology with 3 AS numbers. AS1 is connected to AS2 and AS3. Each of these autonomous systems has 2 routers that are internal BGP or iBGP neighbors. You can see AS1 is originating the 10.1.0.0/16 network because the AS path is empty. The only thing we see is an I for internal origination. The first route has a next hop set, while the second route is set to 0.0.0.0. In this context, that means the route is being originated locally. We can see that this route is selected as the best path because of the caret next to it. We can also see that it has a higher weight, so based on our tiebreaker rules, it wins. Looking at the other networks, we can see that AS2 is originating 10.2.0.0/16, and AS3 is originating the 10.3.0.0/16 network. We can tell this based on the AS path. In this case, we have the top prefix for each entry, which matches our iBGP neighbor. We also saw that in the 10.1.0.0 network. The second entry for each prefix has a different IP listed, and this IP looks like it belongs to the corresponding AS. This must mean that these were received from external BGP or eBGP neighbors, and are a direct path to get to the corresponding AS. Notice that the eBGP routes do not have a local preference. This is because local preference is something that is only advertised inside an autonomous system. You won't see it advertised between autonomous systems. In this example, you might also note that we are using the default behavior and not setting MED at all. The default value when MED is not set is 0, which is the lowest and therefore most preferred value possible. Hopefully this brief overview will give you an idea of what to expect when you run the show IP BGP command. I would not expect this command or output to show up on the CCNA. That said, knowing how to interpret this output is extremely useful if you plan to work for a company that uses BGP in any capacity. You might also find it helpful if you need to use public route servers to see an external view of the internet routing table. Before we move on, I want to review some caveats with BGP attributes that may not seem obvious. First, it's important to remember that despite the massive attributes available, BGP still follows the rules of longest prefix match and administrative distance first. In other words, a longer prefix will win over any shorter prefix from any routing protocol, and a protocol with a lower administrative distance value may be preferred over a route learned via BGP. Second, as we briefly discussed, we should note that some attributes are only advertised on certain types of sessions. Local preference is, well, local, and that means that you won't see it advertised on external BGP sessions. This isn't the case with MED, which can be advertised both internally and externally. A key attribute we didn't talk about in detail is the next hop IP address. As I mentioned earlier, it's important to remember that this address must be reachable by the IGP for a route to be installed. It doesn't matter how you set the other attributes if there's no route to the specified next hop address. Finally, it's worth noting that each AS uses MED differently, and most don't use it at all. For this reason, routers will only ever compare MED between prefixes received from the same autonomous system. Alright, we're starting to get into the more complex BGP topics now. One thing to consider with any routing protocol is preventing routing loops. We talked about AS path briefly, and on the face of things, it seems like that would provide the means to detect a loop, but we'll soon see it isn't quite enough. First, I want to review what a routing loop is and why it might be a problem. In this diagram, R1 knows about some network 10.1.1.0/24. Maybe it's directly connected, or maybe it's learned from another routing protocol. In any case, it advertises that network to R3, who then re-advertises the network to R2, who then re-advertises the network back to R1. The arrows in this picture indicate where each route on each router is pointing. So R3 has a route pointing to R1, R2 has a route pointing to R3, and R1 has the route locally, but also has a route pointing to R2. A problem might arise if R1 loses its original route. Now it's going to see that it has a route to the network it lost via R2, and it may decide to send traffic to that. Further, R1 will advertise to R3 that it can reach the network via R2, who will re-advertise it back to R2, and you get the idea. We end up with a situation where traffic will be forwarded in a loop. Unlike a switching loop where broadcast traffic is duplicated and amplified, routing loops can be very subtle and may not be noticed until a customer calls in with a complaint. The time to live field in the IP header will be decremented and ultimately cause traffic to be dropped, so you won't see congestion like you would in a broadcast storm. One way of ensuring routing loops don't happen in BGP is looking at the AS path. We have a nice list of every AS that a prefix has traversed, so if we see our own AS in the AS path, it means we've already seen that prefix, and we should reject the looped route. Here's the diagram we looked at earlier. You can imagine AS3 attempting to advertise this network back to AS1, and AS1 rejecting it because it sees its own AS number in the AS path. Sounds simple, right? Unfortunately, AS path is only updated when a prefix is advertised to a different AS number. The problem comes when we want to advertise something to a router with the same AS number. We won't update the AS path in this case, so there's no way for a router to determine if it's seen a prefix before, and we're right back where we started. In this diagram, you can see that R1 has two routes to 10.1.1.0/24. One is via its external neighbor, while the other is via its internal neighbor. When the external prefix goes down, we end up with the picture we saw 2 slides ago, with traffic silently circulating between R1, R2, and R3 until it's dropped. Clearly, this re-advertisement is causing a problem, so how do we fix it? The answer is simple: just don't re-advertise. BGP by default has a re-advertisement rule for prefixes learned from iBGP or internal BGP neighbors. The rule is to not re-advertise an iBGP learned network to another iBGP neighbor. This way we can break the loop. So, to summarize, routers will advertise eBGP prefixes to iBGP neighbors. Routers will not advertise routes they've learned from one iBGP neighbor to another. The bad news here is that we now need to make sure the eBGP prefixes are learned by all routers. If we have 3 routers in a row, the middle router wouldn't re-advertise prefixes it learned from the first router to the last router. In order to work around this, network administrators must ensure there's a BGP session between every BGP-speaking router in the autonomous system. Said differently, there needs to be a full mesh of BGP sessions between all BGP speakers in an AS. Keep in mind, though, that BGP runs on top of TCP, so wherever TCP can go, BGP can go too. That, in turn, means that the full mesh of sessions doesn't also require a full mesh of physical connections. As long as there's a route between the IP addresses on either end of a session, things will work fine. And that's where I'll stop with BGP. There's so much more that we could potentially cover, but for the CCNA, this information should be sufficient. I'd encourage you to go out and find more material on your own if you want to dive further into how BGP operates. We discussed that BGP's primary goal is to transfer networks, while the goal for most IGPs is to provide redundancy and full reachability. We talked about how BGP speakers can initiate a TCP session, exchange open messages, use updates to exchange prefixes, use keep alives to maintain session status, and use notifications to alert neighbors of problems. We talked about how BGP uses local preference, AS path, origin type, and MED, among other attributes, to determine the best path to a given prefix. Finally, we talked briefly about the fact that BGP routers won't re-advertise a network learn from one internal BGP neighbor to another to prevent routing loops from forming inside of an autonomous system when autonomous system path isn't updated. Thanks so much for watching this video. I hope you found the information valuable, and I really value your feedback on the content and aesthetics of this video.